Hello, so this is video number 2 of section 5.4. So I want to pick up where I left off at the end of last video. I'd actually originally planned this to go in video 1, but just due to time I decided to start video 2 here. So remember last time we introduced this idea of a matrix M. Right, so if I had a linear transformation from V to W and two bases B and C, where I could take X and represent it as its coordinate vector using basis B, and then take the image of X and represent it as its coordinate vector using basis C, I could find this matrix, right, for T relative to B and C. So I want to start out today with an example of a common type of transformation that we will often look at. And then look at one example of that type of sort of a transformation that fits into this description. So oftentimes we are looking at linear transformations, T, which actually map a vector space to itself. So both the domain and codomain are the vector space V, and what T is doing is just taking a vector X in V and sending it maybe to a different vector X in the same space, right? So you could think of this as like a square, sort of if you're relating these to Rn, Rm transformations, here M, this matrix that's mapping their coordinate vectors, would be a square matrix, right? Because if B was n-dimensional, then each of these would be Rn, right? So because each of these coordinate vectors are represented under the same basis, that basis B is the same dimension. So here, this is sort of like somewhat of an analog of like a square matrix, what a square matrix would do with standard vectors. And so actually often in these cases, as I have in the picture and have as a note here, we'll use then the same basis representations for both the domain and the codomain. So we'll use basis B to represent both the original vectors X and their images T of X. Of course, a lot of vector spaces have many, many different types of bases, and so certainly this type of transformation doesn't have to just have one basis, right? You could have two different bases here, and this would all still work out. But often you're working with the same basis, both in the domain and in the codomain. And so in this case, we have a special name and representation for this matrix M. And so remember what this matrix M is the matrix which takes the B coordinate representation of any vector X and sends it to the B coordinate representation of its image T of X. And so again, what this matrix does is if we have the B representation of T of X, that's equal to this matrix T sub B times X sub B. And this is called the B matrix for T. And this is what it does, is it takes this representation of X and sends it to the B representation, its images B representation. So I want to look at one example of somewhere we've seen this before. So we're going to look at the space of polynomials. And then what we're going to do is kind of return back to Rn and Rm for a bit. And we will finally look at how eigenvalues factor into all of this. So I think we looked at the derivative map a little earlier, but we're going to look at it again. So I'm going to let T mapping the set of polynomials of degree at most 2 to the set of polynomials of degree at most 2. So again, this is a linear transformation between a vector space and itself, be the derivative map. And so remember, because we have the power rule for derivatives when applied to polynomials, this means that we can define this in an accurate, well-defined way as taking the polynomial ax squared plus bx plus c and sending it to the polynomial 2 times ax plus b. So certainly this is a linear transformation. You can show that. We might have shown that before. Again, I think we've looked at this example once before. But so what we eventually want to do now is find a basis, or state a basis for these set of polynomials. And so we're actually just going to let the basis be the sort of standard basis in P2. And so what we want is the B matrix for T. All right, so that is the matrix which would take the B representation of any vector and send it to the B representation of its image. So remember, by definition, this matrix, which we have stated now is represented like this, is equal to the matrix whose columns are equal to the images of the three basis vectors B1 through B3 here. And so these would be the B representations of these images. And so if we're in the space of polynomials, we need to find, basically what this is asking us to find are the derivatives of the three basis vectors. And actually, to go along with, I think, the order I've been using for most of these and the order I have them in my notes, I'm going to reorder these basis vectors. So I'm going to order them B1, which is T squared, so that's B1, B2 will be T, and B3 will be B2 will be T, and B3 will be 1. So we're going to order them. B1 is T squared, B2 is T, and B3 is 1. So notice, since T is just taking the derivative of each of these polynomials, I actually know the images of each of these polynomials. Like so. And so again, we want then the B coordinate representations, right? So I want the vector of length 3 here that represents 2t. Well, so 2t is equal to 0 times t squared plus 2 times t plus 0 times 1, right? And so that's what this vector, which is equal to this vector, is encoding. So that's that. Next, T of B2, which I've labeled as 1, or T. Well, so its image is represented by the following vector, 0, 0, 1. And so finally, T of 1, which is this vector. Well, this is just equal to the 0 vector, so its coordinate representation under this basis is 0, 0, 0. And so remember, sort of just an example reminder here, we say that T of B1, B is equal to 0 to 0, since the vector 2t is equal to 0 times t squared plus 2 times t plus 0 times 1. Right, so basically what we've done is we've taken the three vectors, basis vectors, represented this polynomial 2t as a linear combination of them, and then encoded the coordinates as vectors. And so this would be the B matrix for t, 0, 0, 0, 2, 0, 0, 0, 1, 0. So what we can do with this is actually now calculate derivatives using matrix multiplication. And so I'll show you how to do that. So we can erase everything except for this matrix. So now if we had the polynomial (3x squared minus 4x plus 5) what we want to do is calculate first the B representation of P of x, and then we want to use that to calculate the B representation of the image of P of x, which, remember, the image of P of x is just the derivative. And so what we'll see is that we can take the B representation, multiply it by this matrix, and we'll get what we expect the derivative representation to be. So by definition, I can represent this polynomial in the following way, if I do it correctly: 3, -4, 5. Right? And that's because, again, 3x squared -4x times 5. So now this is equal to the B matrix for T times the B representation of P, which is equal to, well, this matrix here times 3, -4, 5. And this gets me, well, 0 in the first entry, 6 in the second entry, -4. And so remember, this corresponds to the polynomial 6x minus 4. So this vector corresponds to the polynomial 6x minus 4, and you might notice the derivative of this is, in fact, 6x minus 4. So what we showed, basically, we took this vector space, which wasn't Rn, or R3 in this case, found this matrix which could, in a sense, perform this linear transformation for us. And so we showed that taking a derivative is actually just secretly matrix multiplication, at least when we're working with polynomials. Which I've always thought, this type of example was really cool. So anyways, how do eigenvalues factor into all of this? So we're going to let A be an n by n matrix. And we're going to assume that A is diagonalizable. So remember, this is equivalent to stating that A is diagonalizable. This is just the definition. So next we're going to let T of A, which maps Rn to Rn, be the linear transformation defined by A. So what that means, T of A is sending x to the vector A times x. So remember that if A is diagonalizable, we can form a basis out of the eigenvectors of A, right? So next thing I'm going to do is let B be the basis formed by the n linearly independent eigenvectors of A. So what this is a basis for Rn. And remember, we stated already that if A is diagonalizable, we know it has n linearly independent eigenvectors. And from chapter 4, we know that if I have any set of n linearly independent vectors in Rn, which at all times in this case we are in Rn, this gives me a basis for Rn. So now we really are working with two vector spaces here that are just both Rn. And so I can actually do the same thing that I've been doing, where maybe instead of looking at this transformation under the standard basis representation of these vectors, I can use the basis representation defined by this basis B, right? So what I'm doing is creating the same map where I send x down to its coordinate vector, the image of x down to its coordinate vector under this basis B. And as we've been doing, what we want is a matrix which will send this vector to this vector. And as it turns out, if we're using this basis B and A is diagonalizable, the B matrix for this transformation T sub A is this diagonal matrix D. How awesome is that? So if A is a diagonalizable matrix, we can basically, under a different basis, represent this linear transformation as multiplication by a diagonal matrix. And so I'm going to state this formally as a theorem, which is theorem 8. And then I'll talk about it a little bit. So I will say that there's a proof for this in the worksheet, but due to time constraints, I'm not going to talk about it in the video. And so I highly encourage you to look through that proof. I've got an outline of the proof that you can follow, and then I'll post answers sort of to those outlined questions on a when I post the worksheet solutions. And so you can, if you're interested in the proof, certainly you can read it. It's a great, awesome proof where you kind of just work through it all and show that this has to be the case. And so if B is a basis for Rn, the eigenvectors of A which, remember, the eigenvectors of A are just the columns of P, then this diagonal matrix D is equal to the B matrix for the linear transformation T of A, where T sub A of x is equal to A times x. So theorem 8 basically states that this mythical B matrix for the linear transformation T we've been looking for, in the case when I have a diagonalizable matrix, can just be found by looking at this matrix, this diagonal matrix D. And so a few notes here, and we'll look at this example, or you'll see a little more of what I mean, at least part of this, when we look at an example. These two linear transformations, so multiplication by A and multiplication by D, are basically the same linear transformation, just represented under a different basis. Because remember this idea that, like, these pairs of vectors can be thought of as the same vectors, but just represented with a different basis, right? And so, in a sense, A and D represent the same linear transformation, but represented under a different basis. And as we'll see, there are a lot of advantages to looking at linear transformations represented by diagonal matrices, because as we'll see, multiplying vectors by diagonal matrices is very easy, because all we do is just scale each entry by specific entries on the diagonal. And so having this ability, so to say, like, we've got this linear transformation that we can just sort of do this similarity transformation and represent it as a diagonal matrix is very handy. So I want to do one example of this where we're going to basically take a matrix A and take this basis, which I'll sort of give away is going to be the eigenvectors of A. And then we're going to find the B matrix for T and sort of explain through what all of this means. So we want to find the B matrix for the linear transformation T sub A of x, which maps any vector x to A times x, if A is equal to the matrix 5, negative 7, negative 3, 1, and B is equal to B1, B2, where B1 is the vector 1, negative 1, B2 is the vector 3, 7, are eigenvectors of A, corresponding to eigenvalues 8 and negative 2. Lambda 1 equals 8, and lambda 2 equals negative 2, respectively. So B1 corresponds to the eigenvalue 8, and B2 corresponds to the eigenvalue negative 2. So this problem ends up being relatively easy because we know that the B matrix for this linear transformation, which again, remember, is equal to the and so this is sort of where the eigenvalues come in, right? Because remember, this matrix is equal to the matrix whose columns are given by the B representations of these two basis vectors. But remember, these are eigenvectors of A. And so remember, this is equal to the B representation of A times B1 and the B representation of A times B2. But remember, A times B1 is equal to, and I'm kind of giving actually a mini proof for theorem 8 here, A times B1 is equal to 8 times B1, since B1 is an eigenvector corresponding to 8. A times B2 is equal to negative 2 times B2. And so notice, this actually is what implies then that this matrix is equal to the diagonal matrix D described by theorem 8, right? Because A times B1 is just equal to the value 8 times B1. So its B coordinate representation is 8 times B1 plus 0 times B2. B2's coordinate representation is 0 times B1 plus negative 2 times B2. And so certainly you didn't need all of this work, right? You could have just said by theorem 8, if we know the eigenvalues, it has to be 8, 0, 0, negative 2. But this sort of gives like an intuition as to why the proof is true. That because A and D were similar in this way, and this is ultimately what the linear transformation T is representing, this is sort of where we get this idea that the B matrix for T is actually just this diagonal matrix. And so there's one more problem on the in this example that I do want to quickly go over to kind of give a little more intuition again as to what's going on here. So we'll keep in mind that this is the B matrix for T sub A. And we kind of want to finish off with, again, just looking at an example of exactly what this matrix represents. So second part of this, we want to say that if x is equal to the following vector 4, 6, then we want to calculate x sub b and t sub a of x sub b. So I chose an easy vector, so notice that x is equal to b1 plus b2. And so this implies that x sub b is equal to 1, 1. And so next, remember, by definition, the b representation of the image of x is equal to the B matrix for T, which again is this matrix, times the B coordinate representation of X. And so this is equal to the vector 8, negative 2. And so just sort of a quick then like idea of what this vector means. So this is the, again, B representation of the image of X. So we can check our work. By first calculating A times X, which if you multiply matrix A times the original vector X, you get the vector 2, negative 22, right? And so this is equal to the original matrix A times the original vector X. So this is T sub A of X. So what this is saying is that this vector 2, negative 22 should equal where's the B representation? 8 times B1. Oh, sorry, B1 is equal to 1, negative 1. Plus negative 2 times B2, which, working this out, I think is almost correct. Oh, B2, that should be a 7, sorry. 3, 7. Oh, good, okay. I'm not going crazy. This is in fact correct. And so notice this means that this vector has B coordinate representation 8, negative 2. And so notice that one more thing, this matrix being 8, 0, 0, negative 2, notice that what this matrix did to X was just multiplied its first entry by 8 and its second entry by negative 2. And so, like, ultimately that's kind of an indication of why we like diagonal matrices as linear transformations, because they just multiply each entry by a constant value each time. And so you can sort of see the advantage to looking at a linear transformation using a diagonal matrix as opposed to A. So B matrix for T, if A is diagonalizable, is just the matrix D, which is similar to A, under the basis given by the two eigenvectors of A. So, like I said, I apologize. I know that that's like a lot, and a lot of crazy notation. But yeah, so next lecture we will look at just a couple more theorems and then some theory problems.